about Earth. Hello everybody, so today we're going to be looking at the subject of today, which is Earth, and a happy Earth Day and a happy Earth Month to everybody, and get to enjoy this day as we get to also appreciate the natural environment that we have on this beautiful planet. Okay, let's move on to this video. First of all, we're going to be looking at how we are deriving the same axis and the orbital period from Kepler's third law. We have looked at this in many other videos, like the Make video. You can even look at the Mercury video as well. There are a couple of videos, Venus video as well. I think I explained how we derive these expressions, so go and watch those videos as well to get more understanding of how we derive those expressions. But one thing I would like you to also notice is the way the equations change in each and every stage, so that you don't get confused, because you find that the Kepler's third law talks about the relationship between the period and the distance between the planets. You see the t squared over z cubed. You'll find that the actual symbol that's used for the separation between the two masses is an r, not a z, but here you find that I use z. So take note of such things as you go through the derivations. So let's now move on to the same major axis. Okay, so one thing you're going to notice for our calculation here is that we're going to use our initial method of calculating the same major axis, where you say the sum of the perihelion and the aphelion over 2. The aphelion is basically the abscess, which is the longest distance from an object, which is the sun in this case, and then the perihelion is the shortest distance from the sun in the orbit. So at the point where it has the shortest distance is the perihelion, and the point at which it has the longest distance in the orbit, that's the aphelion. So let's look at that method. And before we go, I would also encourage you to use the other expression, that expression that you first saw in the previous slide. Just use that equation or that formula to calculate the aphelion and the perihelion. But we're going to calculate the period just after this. So get the value that we get for the period, and then you can use it to substitute on t in that expression, and then the rest you can find. It's common knowledge, the gravitational constant, which is g, the 6.674 times 10 to the power negative 11, and then the mass of the sun, 1.989 times 10 to the power 30. All that you already know. We've been using it for quite a long time in the videos. So use that equation to prove the answer that we're going to get here for the same major axis. So the idea of the same major axis, I think we already know. It's basically a plus p over 2, as you can see, which gives us the z. Like I said, z is going to represent the same major axis in our calculations. So you'll find that if we were to put the sun in the middle of those two earths that you see in the diagram, like directly in the middle of the center, the distance from the sun to either one side will be like the radius of the orbit. And that's if we were to say that the orbit is in a perfect circle, although we know that because of the eccentricity of orbits that we have looked at prior to this, we know that the orbits are not circular in shape. They're actually oval in shape. They tend to become more of an oval shape than circular shape. So that's why we have the aphelion and the perihelion. But if we were to assume that it was the perfect circle, we'd use this same major axis. So it's more of an assumption that we're dealing with a perfect circle in terms of the shape of the orbit. So we do that, and then we get we substitute the a and the p, then we divide by 2, and then we get our 149,589,023.5 kilometers, and that's in kilometers. Take note of that. So Now I want us to convert these kilometers to astronomical units. You'll find something in most sources. They don't even talk about astronomical units because of something that we're about to see. So 1 meter will be equal to 6.685 by 10 to the power negative 12 astronomical units, right? In that, we use the 6.685 times 10 to the power negative 12 astronomical units. We use proportion, and then we multiply with the what? With the kilometers that we found is our same axis. And then we get 1.000062787. So which means that decimal is negligent. That's why you see that I've approximated it to 1 astronomical unit. And actually, that 1 astronomical unit shows that what? According to that note, it says this shows that the distance between the Earth and the Sun is used to define 1 astronomical unit. So an astronomical unit, 1 astronomical unit, is equal to the distance between the Earth and the Sun, which is basically the same major axis. So 1 astronomical unit is equals to the Earth's same major axis, if you get that point. So everything in astronomical units is based on the what? On the distance between the Earth and the Sun. That's basically the idea behind it. We are trying to make it relative to us because we live on Earth. We are used to our own things, our own distance, our own time. So we're trying to make it relative to our own measurements and our own distances. So I think you get the point. It's a conventional definition. It's not like it's something that you can actually pinpoint. It was more of an agreement to say we're going to define the astronomical unit in terms of that same major axis, so that we have a universal way of looking at the distance, and so that we don't have to look at, if you see it's in kilometers, but still the number is the magnitude is still great. But when you put it in astronomical units, it's now one astronomical unit, so it makes it easier to work with. Now I move on to the Earth's orbital period, and like we saw, that if you bothered to read the Kepler's third law as I was explaining previously, according to Kepler's third law, which states the squares of the orbital periods of the planets are directly proportional to the cubes of the semi-major axis of their orbits. Therefore, Earth's orbital period is what you then see being calculated there. So how do we compute it? We first show the formula that we're going to use, which is t is equal to 2 pi. You know why 2 pi is because we're dealing with a circular orbit, so that should make sense. We are using 2 pi because it's more of a circular shape according to our assumption. Like I said, we're going to use the same major axis, that's why you see the z is there, which means we need to assume that it's a circular orbit for us to be able to get the average or the more accurate figure that we can relate with or we can deal with in our calculations. So the period is equal to that 2 pi, which is the square root of that fraction z cubed over the gravitational constant multiplied by the mass of the sun. So the t will then be equal to, t is the orbital period, but don't be confused. I know I used t here. There's another time we're going to use t again, but it won't be orbital period, so don't get confused with these symbols. So t will be equal to the 2 pi that we substitute the values, same major axis in kilometers, rather in meters now. That's why you see that is by 10 to the power of 3. Then outside the brackets we then put the cube because it's a cube. Yes, and then that will be equal to 31,554,271.58 seconds. And like we normally do in our videos, because now we are mathematically literate, we just do things at once, but I'll explain the shortcut that I've just used here for those who are not able to calculate it, because we're trying to convert to the days that it takes for Earth to move around the sun, to orbit the sun. So what we do is we put it as a single denominator, but you can go in stages where you say that value of t in seconds divided by 60 seconds. We do that in order to convert it to minutes. And then after finding the minutes, you divide those minutes by 60 minutes. That's why you find we have another 60 there. And then we convert that to hours. Then you divide the hours by 24 hours because we have 24 hours in a day. We have 60 minutes in an hour. We have 60 seconds in a minute. That's the idea behind it. And then we divide by the 24 hours and we get the days. But to just sum it up at once, we just say all those values 60, 60 and 24, we just multiply both of them, all of them together, and then we make them one denominator that we just divide into those number of seconds, and then we get our 365.2 114766, and as you can already see, that's coming out as what? The number of days in a year. Very common number, 365 days in a year. 24/7, 365 days in a year, very common statement. So that's our orbital period, 365 days, that we all know are days in a year, but it's actually 365 and a quarter. If you read the fact sheet that was at the beginning of this video, you saw it as 365.25. That 0.25 represents a quarter of a day. It means a quarter. That's the decimal for a quarter, for 1/4. So it's 365.25 or 365 and a quarter days that it takes for Earth to move around the sun. Why we have 365.21 in this case, it might be just a slight change in approximation of the numbers that we used in the calculation, but the normal number is 365 and a quarter, that's known, and for a leap year it will be 366. And we know leap years is basically the year that can be divided by 4 without leaving any remainder. That's basically a leap year, for those who may not be familiar with what leap year is. So now let's move on. Okay, so now we move on to see the relationship between orbital periods of the planets and their respective semi-major axes. So we have been looking at the orbital period and the semi-major axis that we calculated for Earth, and you might be familiar with this graph from the planet Venus video. I think that's when I did it. Yes, it was the planet Venus video, so you might be familiar with this one. If not, then I suggest you go and watch that video. So basically we have our vertical axis being the orbital period in terms of Earth years. Like I said, the convention of the International Astronomical Union is that we use Earth as the standard for the definition of certain quantities that will be used for calculations in the field of astronomy. So that's why we find that astronomical units, it was based on the distance between the Earth and the Sun. Here we are going to be looking at the orbital periods in terms of Earth years, because we're familiar with the time on Earth, so we use that time relative to those other planets, so that it's easier to analyze what we're trying to analyze. Yeah, and to prove that, we are going to see something in terms of the positioning of the point for Earth. So as you can see on that green line, that line graph with the positive correlation, meaning that the Earth years and the semi-major axis in astronomical units, these are log-to-log plots. If you don't know what that is, you may need to just do some research on that. These are not the actual values. It was basically changed so that we can have that those values as our scale up to 1,000, from 0.1 to 1,000. Unless if you're going to look for Earth, for the point for Earth, it might say otherwise. Like for example, we saw that the astronomical unit for Earth, for the semi-major axis of Earth, it's 1 astronomical unit. So we expect Earth to be within 1, and that's exactly what's shown on the graph. And you see that the orbital period for Earth as well, it's 1 year, 365 days, it's 1 year, so it should also be in 1. So where 1 and 1 intersect, that's where Earth is. Basically, that's the idea. And then you find that as we go up that line, we'll see that the period, orbital period for the planets and the semi-major axis from the Sun will increase. That's for these two, but you find that with the eccentricity, it might say otherwise. Okay, so I think we can all agree that with the temperatures that we are currently feeling on Earth, it's a bit different from the normal, because of this global warming and the trapping of heat by the CFCs that have just gathered and reacted in the atmosphere there, which are blocking the heat from escaping. All that is causing the changes in temperatures, which is now affecting our environment. And this is where the black body temperature is needed, because we need to determine what we call the normal temperature. Because the black body temperature, I know I didn't manage to define it in the other video, should be the Jupiter video, which I did. If not the Jupiter, then it's the Saturn video. Just check which between those two videos. You'll find that the black body temperature is basically the temperature of the planet that's felt on the planet without factoring in the heat trapped. That's the heat that is trapped by the atmosphere. So that's why I was trying to explain using what we are experiencing right now, so that you can relate. To say right now we have rising temperatures, which means there was a normal temperature that was expected to be on Earth, to be felt on Earth, but due to this global warming and the trapping of heat, now we're experiencing higher temperatures. So we're saying if we were to remove that excess temperature that is being caused by the trapping of heat, what is the resultant temperature? That's the one we are trying to discover right now, by calculating the black body temperature. That is the black body temperature. So let's look at the calculations. You can read that note at the bottom there, which talks about the Stefan Boltzmann law. You can just look at that and understand more about the energy and the like. But we're going to look at the calculation. That's where we are most concerned. That's where most of our focus is going to be on. We're just focusing on the period. Not the periods. Like you see, I was talking about the T previously. Don't make that mistake. It's the T now is representing the black body temperature. So you see that that black body temperature. Okay, let's look at what's on top there. We have A, which represents the albedo. As you can see in that equation, we have A there, or the formula T is equal to the fourth root of L, which is the star luminosity. For those who don't know, the sun is the star, and it's white in color. So don't think it's yellow; it's actually white in color. I know one of the emojis I used in one of these slides at yellow, but don't be confused. It's actually white. And don't look at the sun directly. Yes, make sure you're wearing some glasses, which might distort the chromatic appearance, but just know it's white. Okay, so now we move on to the denominator, where we have 16 pi multiplied by that sigma, the small letter sigma. It's a Greek letter. For those who don't know, the capital letter sigma, I think you know it. It's that we use the one that's used for to show sums and summations and the like. Yes. So the sigma is basically the Stefan Boltzmann constant. You may want to research who Stefan Boltzmann was, but that's basically the constant that's there, which is also coming from that law that has been talked about there. It's also featured there in that equation, which is that with that funny unit that you are seeing there. But you are going to look at the unit later on. Our main focus is on that 5.670 value that you are seeing there. And then we have the semi-major axis, which is the Z that you can see there, which is squared in that case in the formula that we have. And then we substitute those values into the formula, as you can see, and then we get our 254.0382 kelvins. We just put it to 0.0 kelvins, correct to one decimal place. But we are not so familiar with kelvins. Kelvins is an SI unit. It's a standardized unit that's used internationally. So that's why we've used it there, and it's the one that's normally used for black body temperature and thermodynamics. So we then use degrees Celsius for those who are not very familiar with kelvins. So basically, the rule of the degrees Celsius and the kelvins, there's a relationship between the two. You will find that the absolute zero on the degree scale, it's actually equal to negative 273.16 degrees Celsius for thermodynamic temperature. You'll find that when you extrapolate the pressure to temperature graph, the line graph, when you extrapolate it, which is to extend to the zero line, you find that or at zero pressure, you find that it will be negative 273.16 degrees Celsius. It's actually around 1.5, but yeah, some errors were noted, and then by convention, by universal agreement, 273.16 was then agreed upon as the one that was to be used, or that is to be used by everyone. So that's why we have to say absolute zero is equal to that. So to convert 254.0 kelvins to degrees Celsius, we subtract 273.16 from that temperature, as we see, and then we get negative 19.1218, which is approximately equal to negative 19.1 degrees Celsius. That's according to the NASA fact sheet. If you check the NASA fact sheet, which was edited by Mr. Williams in 2021, you can find the fact sheet on the internet. But basically, the negative 19.1 might be a bit lower than the usual. The usual is around 20 something, I think 23, negative 23, if I'm not mistaken. And if you check the room temperature, in most cases it's around in the 20s. But according to the NASA fact sheet, that's the 20 something degrees Celsius, that's for the room temperature. But the actual one is around negative 19.1 degrees Celsius. So that's the black body temperature for Earth. I hope you get the sense of it. You may be wondering how we determine the units for the term that we'll be calculating. For example, the temperature that we're calculating here, we have found that it's kelvins. We have other things like the same age axis and the period that we're looking at previously. They have their own units, but here we're dealing with kelvins. And as you can see, there is another way in which we can determine that. Of course, one way is we already know that in temperature we have kelvins, which is the SI unit, and then some people may translate that to degrees Fahrenheit or degrees Celsius or whatever the unit of temperature, but the SI unit is kelvins. So we're trying to find out how do we reach the kelvins, how do we find the kelvins. The way in which we can do it is by calculation. So we compute the units that we have. As you can see, we take all the units. Basically, we use the formula. That formula that we use to calculate the magnitude, which is the number or the value, is the same one we use to calculate the unit, as you can see. But what we do is we first eliminate all the constants and numbers without units, and then we are left with those with units, and then we just take the units and position them where their respective terms and quantities are. So as you can see, we have watts, which represents the luminosity L, which is on top in the numerator. We have the other watts per meters squared kelvins to the power 4. That's part of the denominator, which represents the Stefan Boltzmann constant, which has the symbol sigma according to our formula. And then we also have the same major axis, which is in terms of meters, as you can see in the written up there. But in this case, the z in the formula was squared, so our meters would then be squared. And we multiply those two. That's why you see that dot in the middle of those two. That represents the dot product. Basically, we're just multiplying. That's basically what we're doing. And then we put the fourth root, and then we get the unit. So if you can see, we then calculate, we rule out all the like terms, we invert stuff, as you can see. If we have too many denominators, we have to switch the positions in which they are in, as long as we are not violating mathematical principles. If you don't know those mathematical principles, you might need to find that out. When fractions are dividing each other, what happens? Those multiplications and the like, cross multiplication, whatever it's called, all that you need to factor in as you're calculating that. It's basically a simple algebra, but in terms of units, so it might be confusing. And then you find the fourth root of the kelvins to the power 4. Remember, the kelvins to the power 4 according to the Stefan Boltzmann constant, the unit there. So that's why we have that k to the power 4, and then we fourth root, and then we get our k. Basically, we are saying that is how we find the temperature. That's one way in which you can determine. The other way, common knowledge, you already know that kelvins is the SI unit for temperature. But it's best you need to know this thing so that when you find a question which requires you to calculate the unit, at least you know, you have an appreciation of how to calculate the units using the formula that you have been given. You can calculate a unit using the formula you have been given. So let's move on to the next segment. I think is Earth's surface gravity. Okay, so welcome to the Earth's surface gravity slide. I think we can see a lot is happening here, but I'll try to go through everything with you, so don't panic. First of all, let's look at the law that's written at the bottom there. It says, according to Newton's law of universal gravitation, every particle attracts every other particle in the universe with a force that is directly proportional to the product of the masses. The masses, which are the mass of the big object and the mass of the smaller object that are interacting in the space, and the inversely proportional to the square of the distance between them. So the distance between those two masses. And then now let's look at the image that's at the top there, that planet which has been dissected. So as you can see, we have the crust, the mantle, the inner core, which is around 5,000 plus degrees Celsius. It's very hot in there. It's very hot. And then we have the outer core. Basically, that's the structure of the inner part of the Earth. I think those who have studied geography, geology, and astronomy and the like, you know this is very common to you in terms of your studies. So let's now look at how we can relate this law according to that diagram that we have put there. As you can see, we have that green line that's representing the radius. So in the previous videos, I think the Jupiter video, I wanted to put a similar diagram, but I remember I faced some challenges, so bear with me. Now we have the diagram. Yeah, so with Jupiter, I think, and Mars as well, we try to look at gravity and the like, and I think make as well, we try to look at surface gravity. On make, if you watch the make video, I explained this law and what's happening on that diagram as well, but we didn't have this setup of the diagram where it shows the inside, because that green line is going inside the planet, it's not on the surface. On that video it looked like it was going around the surface, like on the surface, which is wrong. Basically it's like going inside. So we were looking at the radius of the planet, so it's more of like the line is going inside, it's cutting inside, as you can see. So we have a blue dot at the inner core there. If you look closely, there's a blue dot that's there, and then we have a yellow dot on the surface at the end of that green line. The yellow dot represents the point mass, which is explained in this Newton's law of universal gravitation. Then the blue dot represents the mass of the Earth, the entire mass of the Earth, which is concentrated at that point, at the center of Earth. What we are trying to assume here is that the separation of the point at the surface of the Earth, of the point mass at the surface of the Earth, is the radius of the Earth, such that the mass of the Earth, because we need to factor in the mass of the Earth, so we have to assume that all the mass of the Earth is at the center of the planet. Hence we have that blue dot there, and we're going to use that in our assumption, so that we can use our radius in our calculations. It's an assumption, it's not like that's where the mass is, but we are trying to make the radius of the Earth as the separation of the two masses, because we are looking at an object which is on the surface of Earth, which is quite impossible for us to then say we use the mass of the Earth, and then we are trying to look at the distance between the surface of the Earth and the point mass on Earth. It's negligible, so it's better we assume that all the mass is concentrated at the center of Earth. So I hope you have understood that. Make sure you understand that, otherwise the equation that we're going to look at next might confuse you, and the law of Newton's Newton's law of universal gravitation won't make sense if you try and apply something different from what I've just said. So now let's look at the formula, which says F is equal to capital letter G multiplied by capital letter M multiplied by the small letter m. So those two m's are different because of the differences in the size of the masses that are separated by that distance between them, according to that Newton's law of universal gravitation. And then all that is divided by r squared, which is the square of the distance between the masses, is stated in the law. So all what you're saying there is what's stated in the law. So you can already see where g is the gravitational constant. We have that, which is 6.674 times 10 to the power negative 11. I don't know the unit, you just find the unit. So the larger m is now the mass of the Earth, which is at the center, at the blue dot. And then the small m is the mass of that yellow object, the point mass on the surface of on the surface of Earth, so that r becomes the distance between the 2 points, which is the radius of Earth, and then we square it. I hope that makes sense. So you may be wondering where the gravity then comes into this whole situation, because we're looking at the capital letter G, and that's a symbol for the gravitational constant and not the gravity that we're trying to look for. So what we have to assume is that this force that is felt by this object on the surface of Earth is the same force that is the same force that pulls the object to Earth, that pulls the yellow object to Earth, and hence we then include mg. Mg is coming from ma. F is equal to ma. If you haven't watched the forces and motion video, which is on the Shumbafoot Creative Space YouTube channel, you might need to watch that video. It explains this mg ma thing that I'm talking about. But basically, we factor in this ma, which comes from the Newton's second law of motion, which says that the force is directly proportional to the acceleration of the object, of the mass, and hence we then get that equation F is equal to ma, which is mass times acceleration. the mass of the object moving at a certain force with a certain rate, which is the acceleration. In this case, we're looking at the downward force, which is the force which moves towards the earth, which brings this mass towards the earth, which is g, which is the gravity. So we then equate the other side of the, so we're saying the force is the same, the force which we calculate using Newton's law of universal gravitation, and the force that we calculate using the Newton's second law of motion, that force is the same. Hence we are equating both expressions, the mg and the gmm over r squared. And then we then rearrange everything and we get our g, which is equal to gm over r squared. If you were to use the F is equal to ma, your unit can be newtons per kg. You are going to see that coming later on when you look at some graphs, some certain graphs that are going to analyze a bar graph. You find that one of the units is newtons per kg. It's because when you rearrange F is equal to ma, when you're looking for a, or you're looking for g in this case, it becomes g is equal to F over m, which is the force over the point mass, or the mass of the object, which is experiencing that force. And that will give you force is in newtons, mass is in kg, so it becomes newtons over kg. That's one of the units that you can use. And another unit is meters per second squared. It's because acceleration is equal to speed over time, so that's why it becomes meters per second squared, and speed is equal to distance over time, so it's basically distance over time squared. That's why you get m over s squared. Okay, apart from that, I was trying to also show you how else you can also calculate the unit, like we did with the temperature there when we were looking for kelvins. So now we have g is equal to capital letter gm over r squared. We already know what that means, and as you can see, the values are now substituted in the gravitational constant, the mass of earth, which is that one, over the r squared. Now r squared, remember I said these two masses are those two dots which are separated from each other. That's how we're going to interpret that diagram and how we're going to interpret the Newton's law of universal gravitation in our case. And that means we're going to use the radius of earth as the separation between the two masses, because we've already defined the two masses as those 2 points, those 2 point masses at the center of earth and on the surface. So that's clear enough. And then we get our answer as 9.8198, which is equal to 9.82 correct to 3 significant figures, which might not be a bit accurate. It's a bit inaccurate, but it's very precise, very close to the answer that we need, which is around 9.81, which is the usual one. But the universal average is around 9.8 meters per second squared. If you take all values that are calculated by people on the surface gravity of Earth and you find the average of all those values, you should get something like 9.8 meters per second squared, or 9.8 newtons per kg. So that's basically the acceleration due to gravity, or the surface gravity of Earth. Very common to physicists and other people who actually deal with this value or this quantity. So I think we have proven that, and how we calculate it using some first principles, laws, and other crucial constants. But one comment that I also want to just pass on the diagram we have here, I sometimes wonder, was I to include that temperature, 5K plus degrees Celsius, more than the temperature that can melt you as a human being, that can kill you. So sometimes I wonder, we are suffering from this climate change, which is caused by the trapping of heat in the atmosphere. Sometimes I wonder, we are crying about this temperature that is trapped, the rising temperature beneath the ozone layer, which is being trapped by those greenhouse gases, and yet we have a greater temperature that is burning down there underneath our feet. It's just that the crust is very thick and is protecting us from experiencing such heat, and we have to appreciate that. Maybe geologists can help us to understand more about it and how that happens, because if that heat was to contribute to the increase in temperature in our atmosphere, our existence would have been at stake, like one of our videos said here on the Shumbafoot Creative Space YouTube channel. But nonetheless, let's move on. Okay, I believe it was the two planets, or dwarf planet Eris, I think, if I'm not mistaken. I'll need to confirm, but just confirm. Around, I think, dwarf planet Eris or two planet Jupiter, between those two videos, I asked you to calculate the surface gravities of other planets that we hadn't covered, and also look at those for the planets we had covered, just the surface gravities, and then you construct your own bar graph of the gravities in the solar system. I hope you did that. If you haven't, please try that. Okay, so what I expected you, in case you're lazy, so let me just explain. What I expected you to have is your vertical axis being the gravity, and like I said previously, as aforementioned, those are the two units that you can express your gravity in. So that's it, and then you put your scale. I used differences of 5, so it's 0, 5, 10, 15, whatever, going to 30, moving upwards. I think you already saw that in one of our shorts on the YouTube channel. And then on the horizontal axis we have the planets. So each planet is there, so that's where we're going to see the bar graphs emerging from those planets and going to their respective positions. And then we have the Earth highlighted there in blue, and the 9.8 that we calculated. So now let's look at the bar graphs which are shown here. So as you can see, so it should be the Jupiter video where I said you should construct this bar graph. This is exactly what I expected you to have, where Jupiter's gravity is more than twice that of Saturn, and we find that it's very tall, the bar, which shows that there's around 24 point something, close to 25 meters per second squared, or newtons per kg. And then we find Earth there is very low. It's probably the fourth. It has the fourth greatest what's it called, gravity compared to other planets. It is the fourth. I think that's true. If not, please correct me, but that should be true according to how I'm seeing the graphs here. You see the importance of representing data according to our statistics video, so that you can see the differences and all that, so that because you see some values are very similar to each other, so you need to represent that data, and that's how we represent the data. So most gravities fall around 10 meters per second squared, or 10 newtons per kg. It's around there. Most of them are close to that gravity. And then we have Jupiter, which is far extreme there, and then so our mean should be around 10, if I'm not mistaken, or around 9 point something, if I'm not mistaken. If you then draw your normal distribution and all that, you can then see how those gravities look like and how they relate in terms of their values. That brings a better understanding of the distribution of the gravities. But if you also maybe draw frequency polygons, that can also help. But basically, you can see that it's not like there's a uniform correlation of the growth in gravity as you move away from the sun, like we saw with the orbital period and the semi-major axis in one of those graphs that we looked at. So you can see that the relationship varies as we move from one planet to another. But the bottom line is most of them are near 10 meters per second squared, or 10 newtons per kg. That's where most of them lie. That's how I expected you to come up with your graph. Mine might not be very accurate in terms of the values. Some are approximated to the whole number, so just bear with me on that if you can make it more clearer with yours. But that's basically what I expected to see. I didn't intend this video to be very long, but you know, it's better that you get to understand more of our planet in this video, since it's Earth Day. It's a very special day for us in Shumbafoot, because we also get to appreciate the environment, the natural environment, apart from this space stuff, but also realize that this is home for us. Earth is home for everyone, and hence we need to understand home more than any other place which is far away. I think that's very important, and I hope everyone will get to understand more about Earth and the activities that happen on Earth, and the relationship of Earth in the universe with other planets, even in the solar system and beyond. So I hope you have enjoyed the calculation section. Now you are going to learn more about the Earth and its environment and how it affects human beings, because this is home for us, so we need to understand more of that, like I said. I hope to meet you next time with another video in our planet series. I'm not going to promise which planets, I'm not yet sure, so I'll update you in due time. But this is To Earth and Beyond. I hope you have enjoyed. Cheers till we meet next time. human beings on planet Earth.
I like to be educated, but I'm so frustrated. Hello to my loneliness. I guess that ignorance is bliss. Take me back to before I knew. Rewind, take it out of cue. Innocence can be a young man's game. Signed up for the hall of shame. I wish I knew how much I miss not knowing that we're all screwed when we play our roles and ignore the problems. I like to be away in my patience. Stay up, I feel so outdated. How can we look the other way? Sun is out, but the sky is gray. What would happen if I took a chance? It's always hard at first glance. I don't wanna, but I know I gotta do it.
The environment on Earth.
This hard to swallow, I think I'll chew it. I wish I knew how much I miss not knowing that we're all screwed when we play our roles and ignore the problems. I wish I knew how much I miss not knowing that we're all screwed when we play our roles and ignore the problems.
Good day everyone, I'm out here in the wild admiring this natural view, and I would like to encourage you this Earth Month as we celebrate Mother Earth and a beautiful environment. I would like to encourage you to conserve the environment in order to preserve the lives of our dear flora and fauna. Take care.